Hey everyone, and welcome back to The Deep Dive. We're tackling a massive topic today, one that literally underpins humanity's entire journey into space. Energy, how we generate it, how we use it, that really dictates how far we can go and, well, what we can truly achieve beyond Earth.
It really is the lifeblood. From, the earliest satellites to probes exploring the farthest reaches of our solar system, reliable energy is just fundamental to every single mission.
Absolutely. And today, we're taking a deep dive into space solar power. Now, this isn't just about how solar tech powers our current missions, important as that is. It's also about this truly audacious long-term vision, beaming energy back to Earth from orbit.
Sounds like sci-fi, doesn't it?
It really does. But consider this your shortcut to being genuinely well-informed on this exciting and, frankly, rapidly evolving field. We're going to unpack these dual frontiers of space solar solutions, reveal some surprising facts, and really help you grasp the most important insights from the research we've explored. Ready?
Let's do it.
Okay, so let's start with that grand vision. Space-based solar power, or SBSP. For many, like you said, it still sounds like something pulled straight from a novel, but the core concept is actually quite elegant, isn't it?
It really is, fundamentally. So SBSP involves collecting solar energy way up in orbit with these massive platforms, often called solar power satellites, or SPS, and then transmitting that energy wirelessly, typically via microwaves or maybe lasers, down to specialized receiving stations here on Earth, which we call antennas.
Antennas, okay.
Yeah. At its heart, it's really a three-step process: collection up in space, conversion and wireless transmission, and then finally reception back on the ground.
And this isn't exactly a brand new idea, right? So what's the origin story here? It goes back a ways.
Oh, it stretches back much further than most people think. We're talking like 1923, when the Russian theorist Konstantin Tsiolkovsky proposed space-based mirrors. Then Isaac Asimov in 1941 wrote a science fiction story called Reason that actually featured a solar power satellite beaming energy using microwaves.
Wow, Asimov.
Yeah. But it was really NASA engineer Peter Glaser in 1968 who gave it a firm engineering foundation, even getting a patent in 1973 for his microwave transmission method.
Okay, so if the concept's been around since, well, Tsiolkovsky and Asimov and Glaser in the 60s and 70s.
Yeah.
Why didn't it become a reality decades ago? What was the holdup?
Well, throughout the 1970s, NASA, the Department of Energy, even the European Space Agency, they all studied it pretty extensively, and they concluded the physics was sound, the basic principles worked, but the cost of launching the necessary hardware into orbit was just, monumental, astronomically high, you could say.
Right.
It simply wasn't economically feasible with the rockets we had back then, just way too expensive to get all that mass up there.
But the underlying idea, the value proposition, it's incredibly powerful.
Yeah.
So why is SBP generating so much excitement now? What makes it so compelling today?
Well, the biggest draw, I think, is that it fundamentally solves the intermittency problem. The issue that terrestrial renewables like ground-based solar and wind always face.
All right, the sun doesn't always shine, the wind doesn't always blow.
Exactly. But imagine a satellite in geostationary orbit. It's bathed in sunlight over 99% of the year. That means continuous 247 baseload power, totally unhindered by night or clouds or atmospheric conditions, constant power.
And the sunlight itself is actually, stronger up there too, isn't it? More intense.
That's right. Solar irradiance, the power per unit area, is about 1,366 watts per square meter above the atmosphere. Down here on Earth's surface, it's more like 1,000 watts per square meter on a clear day.
So more constant and more intense.
Precisely. That combination means a space-based array could generate, maybe 8 to 10 times more energy annually than an identical array sitting on the ground. So proponents see it as this potentially transformative solution for global energy needs and greenhouse gas emissions with maybe a minimal environmental footprint here on Earth itself.
Okay, so what's fundamentally different now that's allowing this resurgence? What changed?
It's really a complete paradigm shift in the space industry. The number one catalyst is the dramatic reduction in launch costs, largely thanks to reusable rocket technology pioneered by companies like SpaceX. That single economic factor just cracked the whole case for SBSP wide open again.
But it's not just about cheaper rides to orbit, is it? There must be more to it.
No, that's just the start, really. This shift is amplified because other critical enabling technologies have matured at the same time. We're seeing, much higher performance photovoltaics, really advanced autonomous robotics for building things in space, and proven wireless power transmission techniques.
So it's a convergence.
It is. So the renewed global pursuit of SBSP, it's more than just about clean energy. It's a clear signal that the whole commercial space ecosystem has evolved to the point where building large-scale, persistent industrial infrastructure in orbit is becoming thinkable. Its viability, in a way, is kind of a proxy for the overall health and capability of the entire space industry.
Okay, that's the grand long-term vision, huge potential. But it's really important, I think, to differentiate that from the immediate reality, which is that solar power is already the absolute indispensable workhorse of space exploration right now.
Oh, absolutely. You're spot on. It's fundamental today. Virtually every spacecraft operating in the inner solar system relies on photovoltaic solar panels. They provide the power for, well, everything, essential systems like sensors, heating, telemetry, all the scientific instruments. And crucially, they generate the high levels of electricity needed for advanced propulsion, like solar electric propulsion or SESIP.
And the history of this side of things, the practical side, it traces back to the very dawn of the space age. It's a fascinating story in itself.
It really is. Vanguard 1, launched way back in 1958, was the world's first solar-powered satellite. Its tiny little silicon cells proved Dr. Hans Ziegler's revolutionary concept that using solar cells to continuously recharge a battery pack was far more sustainable than just relying on finite battery life.
A simple idea now, but game-changing then.
Totally game-changing. That single demonstration basically set the standard for almost every mission that followed in the inner solar system.
And we see that foundational legacy in action today with some truly iconic examples, don't we?
Absolutely. Look at the International Space Station, the ISS. It has these 8 massive solar array wings that together span the area of an American football field. Huge. And they generate up to 120 kilowatts of power.
Wow.
And then for deep space, think about NASA's Juno spacecraft. Even way out in Jupiter's orbit, where sunlight is like 25 times weaker than it is here at Earth, it still generates 500 watts of power from 3 huge 30-foot-long solar panels. It's just a testament to how far the technology has come.
But there's still a fundamental limit, a boundary to solar power, isn't there? Especially as you venture further and further out into the solar system.
There is, yeah. It's down to the inverse square law. Physics gets you every time. As you travel farther from the sun, the available solar radiation just diminishes dramatically. It falls off at the square of the distance.
So double the distance, 1/4 the sunlight.
Exactly. So beyond Jupiter, and for some missions even past Mars, sunlight just becomes too faint for current photovoltaic tech to generate enough power from a reasonably sized array. That's why you see spacecraft like the Voyager probes relying on RTGs, radioisotope thermoelectric generators. They use the heat from decaying radioactive material, plutonium usually, to produce electricity.
Yet we're constantly pushing that boundary outwards, aren't we? Trying to make solar work further out.
We definitely are. Continuous improvements in solar cell efficiency and array design have enabled missions like NASA's Lucy probe. It's using solar power for its journey all the way out to the Trojan asteroids, which share Jupiter's orbit. That's a feat that would have been considered, well, pretty much impractical just a decade or so ago.
And this really highlights what engineers call the power budget constraint, doesn't it? Everything comes down to how much power you have.
It absolutely does. Think of it as the literal electrical lifeline of a spacecraft. Its capability, what it can do, is fundamentally dictated by the electricity it can generate. More power means more science, higher resolution data, greater maneuverability, better communications. The entire evolution, from Vanguard 1's simple little cells to the ISS's sophisticated multi-junction arrays, it directly chronicles our expanded ability to operate effectively in space. And especially with things like solar electric propulsion, SESFI, every single watt per kilogram improvement you can squeeze out directly translates into a more capable, more ambitious, and ultimately more scientifically valuable human presence out there.
Okay, so from that grand, ambitious vision of SBSP to the immediate, indispensable reality powering missions today, it's clear solar power is just fundamental to our space aspirations. But what are the actual technological breakthroughs turning these ideas into, well, reality? Let's dive into the cutting-edge science, starting with the very heart of the system, the space solar cell itself.
Yeah, this is really a story of relentless innovation. It's all driven by the need for more power in smaller, lighter packages because launch mass is everything. The first generation, the stuff that powered the dawn of the space age, was crystalline silicon.
Like Vanguard 1 used.
Exactly, Vanguard 1 used them. But their efficiency was pretty modest, maybe 15-20% back then. And a big issue was they degraded significantly from radiation exposure in space. You could lose maybe 5–10% of their power output per year. You really had to account for that decay in mission planning.
Okay, then we saw a significant upgrade, I think, in the 1980s.
That's right. Gallium arsenide, or GAs, emerged as a superior material. It was inherently more efficient, reaching maybe 20–28%. And crucially for long missions, it was much more resistant to degradation from space radiation. Hardier stuff.
Right, and the current state-of-the-art, the kind of thing you'd find on, say, the International Space Station today.
That would be multi-junction, or MJ, solar cells. These things are incredibly sophisticated. Imagine stacking different semiconductor layers, like in a sandwich, where each layer is precisely tuned to capture a different color, a different part of the solar spectrum.
Different wavelengths of light.
Exactly. This dramatically reduces energy loss and allows them to achieve incredible beginning-of-life efficiencies, sometimes 30% up to even 47% in the lab. And they have excellent radiation hardness, typically losing less than 1% of performance per year. The trade-off, of course, is they're much more complex and expensive to manufacture.
That is a staggering jump in efficiency. 47%. It really makes you consider what these improvements mean for what humanity can actually achieve out there. It's not just, a few percentage points. It's a complete game changer for mission capability.
It absolutely is. It means missions can go further, last longer, gather unprecedented amounts of data. It just makes previously impossible science now achievable. But even with those impressive gains, the scientific community is always looking for the next big disruptive material. And that brings us to perovskites.
Ah, yes, perovskites. Tell us about the perovskite revolution. Why are they causing such a stir? Why are they seen as this potential disruptive contender?
Well, perovskite solar cells are incredibly exciting for space applications for a few key reasons. First, they offer an exceptionally high power-to-weight ratio that's huge for space.
Lighter is always better.
Always. They're also compatible with flexible substrates, which opens up all sorts of new design possibilities for deployable structures. And they have the potential for really low-cost manufacturing, maybe even printing them, like newspaper.
Wow, printing solar cells.
Yeah. And here's where it gets particularly interesting for space. Early research shows they have remarkable resistance to space radiation. Some studies even suggest they might have self-healing properties after taking some radiation hits.
Self-healing. That does sound like something straight out of science fiction. Are they actually testing these in space already?
They are, yeah. Just recently, in July 2024, perovskite tandem solar cells, that's perovskite layered with another material like silicon, were launched on a small CubeSat for in-orbit testing. In labs, these tandem cells are already achieving over 30% efficiency.
Okay.
But perhaps the most revolutionary concept tied to perovskites is something called moon glass. Researchers have actually demonstrated making a type of glass substrate directly from simulated lunar regolith, basically, moon dust.
You're kidding?
Nope. And the idea is you could then fabricate perovskite cells directly onto this moon glass on the moon. Imagine producing vast fields of solar cells right there on the lunar surface, dramatically reducing the amount of mass you have to launch from Earth for future lunar bases. It's a huge potential advantage.
That's an astonishing vision, making solar panels from moon dust. But okay, there must be a catch, right? What are the significant challenges facing perovskites?
The primary drawback, the big hurdle right now, is long-term stability. While the vacuum of space actually helps because it eliminates moisture and oxygen degradation, which plagues them on Earth, they're still potentially vulnerable to the extreme thermal cycling in space, going from super hot to super cold, and also the unfiltered UV radiation.
Right.
So proving that these cells can maintain stable performance for years, not just days or months, that's the critical step needed for widespread adoption in space.
So it sounds like perovskites aren't just a new material. They represent a whole new philosophical approach to designing space hardware, don't they?
That's a great way to put it. What's fascinating here is that the traditional approach, with those expensive multi-junction cells, prioritized extreme durability and perfection. Because launch costs were sky high and repairs were basically impossible, you built it to last, period.
Right, build it once, build it perfectly.
Exactly. Perovskites offer a potentially different model. They might be cheaper and easier to manufacture, maybe even in space eventually. This opens the door to mass production and, crucially, flexibility. With low-cost launch becoming a reality, and with emerging in-space servicing and manufacturing ISAN capabilities, maybe deploying vast fields of cheaper, replaceable panels becomes more economically viable than building one single, hyper-expensive, unbreakable array. This potential shift from an artisanal, bespoke model to more of a mass-production, disposable model is why they're being watched so closely.
That philosophical shift is truly profound. Disposable solar panels in space.
Okay.
But even with the most efficient cells, whether they're perovskite or multi-junction, you still have the challenge of getting them to space, and then once they're there, unfurling them to enormous sizes. This brings us to advanced deployable arrays.
Right. The fundamental conflict is always how you fit those large power requirements, those huge surface areas, into the very limited volume you have inside a rocket fairing. That's where deployable arrays are essential. They let you pack a huge blanket of solar cells into a relatively small space for launch.
And the leading innovation here, the one getting a lot of attention, is the Rollout Solar Array, or ESA.
Redwire's RSI is a really ingenious solution. Instead of using traditional rigid panels that fold up like an accordion, RSI is basically a flexible photovoltaic blanket that rolls up kind of like a measuring tape or a window shade.
Okay.
It's supported by these thin composite booms that are flattened and rolled up for launch. Once in space, they use their own stored strain energy to unfurl and become rigid, deploying the blanket without needing heavy motors. This design is remarkably efficient. It's about 20% lighter and stows in roughly 1/4 the volume of traditional rigid panels. That's a huge advantage for saving mass and launch cost.
And Ornisa isn't just a concept, right? It's already flight-proven and operational.
Oh yeah, absolutely. The larger version, called IR-Aroas, is actively augmenting the power system on the International Space Station right now. They've installed several pairs. It also successfully powered NASA's DART mission, the asteroid impactor, demonstrating its reliability way out in deep space. Its high power to mass ratio makes it pretty critical for enabling future high power solar electric propulsion systems that need to generate a lot of electricity but still fit inside a rocket.
Are there other notable innovations in deployable arrays worth mentioning?
Briefly, yes. A company called Space Tech has developed a clever multi-hinge mechanism for deploying large, rigid panel arrays, which has been used for constellations like OneWeb. And Airbus offers something called Sparkwing, which is more like a commercially available, modular, off-the-shelf array system specifically designed for small satellites. It helps reduce lead times and costs for missions needing anywhere from, say, 100 watts up to about 2,000 watts. So lots of innovation in how we actually unfurl the power once we get it up there.
Okay, so we've got the power collected by advanced cells, unfurled by these clever deployable arrays. Now, for that ambitious space-based solar power vision to work, that energy needs to get from orbit all the way down to Earth, which means beaming power across the void. Let's talk about wireless power transmission, or WPT.
Yeah, WPT is absolutely essential for SBSP to ever become a reality. Without efficient wireless power transmission, the entire concept just, stays grounded, quite literally. There are two main methods being seriously pursued.
Okay, and the most mature approach, the one with the longest history, is microwave power transmission. Tell us about that. How does it work?
Right, so this approach basically takes the DC electricity generated by the solar panels on the satellite and converts it into radio frequency energy, specifically in the microwave band. It's typically around 2.45 gigahertz, which is a frequency chosen because it passes through Earth's atmosphere really well, actually similar to the frequency your home Wi-Fi uses.
Oh.
This microwave energy is then beamed down by a very large phased array antenna on the satellite towards a dedicated ground receiving station, the rectenna. And we've seen historical demonstrations of this going way back. William C. Brown powered a model helicopter with microwaves in 1964.
No way.
Yeah. And in the 1970s, JPL and Raytheon successfully beamed 30 kilowatts of power over a mile. More recently, a major milestone came in 2023 when Caltech's Space Solar Power Project successfully demonstrated detectable power beaming from orbit down to Earth, a huge proof of concept.
What are the main advantages and, I guess, the drawbacks of using microwaves for this?
Well, the big advantages are that microwaves can pass through clouds and rain, making it an all-weather, reliable option for continuous power delivery. And importantly, the power density of the beam hitting the ground can be engineered to be safe, no more intense than the midday sun, potentially even less.
Okay, that's crucial for safety. What about the downsides?
The main drawback really comes down to basic physics, diffraction. The beam naturally spreads out over the vast distance from geostationary orbit to Earth. To keep it focused tightly enough on the ground or antenna, The transmitting antenna in space has to be enormous. We're talking on the order of a kilometer in diameter.
Kilometer.
Yeah, and the ground antenna needs to be even larger, potentially several square kilometers in area. This massive scale drives very, very high infrastructure costs, both in space and on the ground.
Okay, kilometer scale antennas, that's huge. What's the alternative to microwaves then?
The main alternative being explored is laser power beaming, using lasers instead of microwaves. Its key advantage is much higher directionality. Laser beams spread out far, far less over long distances.
So you wouldn't need such giant antennas.
Exactly. This could allow for significantly smaller and potentially cheaper receiving stations on the ground, and maybe even smaller power beaming satellites operating from low Earth orbit, which is much closer than geostationary orbit. Sounds promising, but I'm guessing there are significant disadvantages here too. Lasers from space sounds complicated.
You're right, there are two major ones. First, unlike microwaves, laser light is easily absorbed and scattered by clouds, fog, rain, even atmospheric dust. This makes it inherently unreliable for providing continuous all-weather power needed for baseload electricity.
So it's fair weather power only.
Pretty much. Second, and this is a really crucial point, there are serious safety and geopolitical concerns. A high-powered laser beam directed from orbit has obvious potential as a weapon. The risk of accidental or even intentional misuse, like blinding pilots or damaging satellite sensors, is a significant regulatory and diplomatic hurdle. It would require very careful international treaties and verification regimes.
Yeah, that dual-use potential is a huge issue. So given all these steps, converting sunlight to DC, DC to microwaves or lasers, beaming it, converting it back, the entire economic case for space-based solar power really hinges on the end-to-end efficiency of this wireless power transmission, doesn't it? Precisely. It's a whole chain of energy conversions, and each step has associated losses. You lose a bit converting sunlight to DC, you lose more converting DC to RF energy, you lose some in atmospheric transit, and you lose some converting the RF back to usable electricity on the ground.
Right.
While the theoretical maximum efficiency for microwave WPT is often estimated somewhere between 50 and 80%, current real-world experiments are still down in the 10 to 15% range for the whole system, though the rectennas themselves can be very efficient, over 85% in labs. So maximizing that overall end-to-end WPT efficiency is probably the single biggest technical challenge that will ultimately decide whether SBSP is economically viable or just a cool science experiment.
Okay, so we've explored the technologies, the physics, the challenges of beaming power. Now let's look at the incredible ecosystem of players actually trying to make all this happen.
Yeah.
It's a mix of established giants and nimble startups.
Right. It really is a fascinating mix. You've got these huge established aerospace and defense companies, and then you have these much newer, often venture-backed startups. And each player, whether they're a long-standing titan or a new entrant, is playing a distinct and pretty crucial role in advancing the whole field.
Okay, let's start with the titans of industry. Who are the big established players making moves in space solar?
Well, you've definitely got Northrop Grumman. They're a premier U.S. defense and aerospace company, heavily invested in all sorts of space systems. They're a prime contractor for the U.S. Space Development Agency, building dozens of data transport satellites that, of course, rely on robust solar power.
Right.
But beyond just using solar power, they're actively developing wireless power transmission technologies specifically for SBSP applications. They've completed ground tests and are apparently aiming for a space-based demonstration sometime around 2025. Their focus, naturally, tends to be on high-value national security applications first.
Okay. Across the Atlantic, we have Airbus, who seem to have a really broad strategy here.
Yeah, Airbus is interesting because they have this very comprehensive, multi-pronged solar strategy. On one end, they manufacture components like their Sparkwing modular arrays for small satellites, and also the large deployable arrays for big constellations like OneWeb. But they're also a key player in Europe's push for SBSP. They're involved in ground demonstrations and have developed concepts for a huge 2-gigawatt satellite system, framing it as crucial for future European energy independence. And they even developed the Zephyr, which is this solar-powered, high-altitude pseudo-satellite. Think of it like a super long-endurance drone that flies so high for months at a time, it's almost like a satellite itself. Solar-powered, of course.
Zephyr, right. And then there's Boeing, but specifically through its subsidiary Spectralab, which is a huge name in cells.
Absolutely. Boeing, primarily through Spectralab, is really a foundational pillar of the entire space solar industry. Spectralab is one of only 2 U.S. companies that produces the absolute highest performance space-grade solar cells, the really top-tier stuff.
The multi-junction cells we talked about earlier.
Exactly. They pioneered those multi-junction cells and still hold world records for efficiency over 40% using concentrators, and routinely hitting 32-33% for their production-level cells that fly on countless missions. So Spectralab basically acts as a premier component supplier to, well, virtually the entire satellite industry. They're incredibly influential behind the scenes.
Okay, now let's take a specific deep dive into a company that really embodies the whole new space approach and what it means for solar power. Rocket Lab. Their vertical integration strategy, bringing solar cell production in-house, is particularly fascinating in this context.
Yeah, Rocket Lab really epitomizes that new space agility and rapid innovation. A truly pivotal move for them was their acquisition of Solero Holdings back in 2022 for about $80 million.
Right, I remember that.
This was a hugely strategic play because it brought one of only 2 US-based manufacturers of those high-efficiency, space-grade solar cells directly in-house. Rocket Lab's CEO, Peter Beck, explicitly stated the rationale. It was about transforming Rocket Lab from just a launch provider into an end-to-end space company. Owning the solar cell production helps them reduce costs, shorten satellite build times, and crucially de-risk their entire supply chain.
So they control a key part of the satellite now, not just the ride to orbit. And this acquisition has allowed them to develop a pretty sophisticated and impactful portfolio of solar products, hasn't it?
It absolutely has. Their flagship solar cell is called the IMM. It boasts a remarkable 33.3% beginning of life efficiency, which is top tier, and it's engineered to retain 87% of its power even after 15 years soaking in space radiation that's crucial for long duration missions.
Wow, 15 years.
Yeah. And building on this cell technology, they're launching a new product line called the Star Ray family in 2025. These are customizable modular solar arrays ranging from 100 watts up to about 2,000 watts, basically offering plug-and-play power solutions tailored for the rapidly expanding small satellite market.
And the practical impact of this vertical integration strategy, bringing Solero in-house.
Yeah.
It's pretty clear already, wouldn't you?
Oh, it's undeniable. Get this. Over 1,700 satellites currently in orbit are powered by Rocket Lab technology, thanks to that Solero heritage.
1,700.
Yeah. They've been selected for super high-profile missions like the James Webb Space Telescope, components for NASA's Artemis lunar program, the Ingenuity Mars helicopter. Even Firefly's Blue Ghost lunar lander will use their arrays. They're also a key supplier to Airbus for the OneWeb constellation. And critically, this in-house capability directly helped them secure that landmark $515 million contract from the U.S. Space Development Agency to build 18 complete military satellites. It really demonstrates how vertical integration can transform a company from just a component supplier or launch provider into a prime contractor for major government space initiatives.
That's a powerful example. Okay,
Yeah.
so beyond these established players and vertically integrated companies like Rocket Lab, there's this whole new vanguard emerging.
Yeah.
Lots of nimble startups and ambitious government initiatives really pushing the boundaries of space solar, especially on the SBSP front.
Yeah, this creates a really dynamic ecosystem. It's fascinating to watch. Many of the SBSP-focused startups are cleverly targeting niche applications first, rather than trying to, solve the entire global energy grid problem right out of the gate. For example, there's a company called Space Solar in the UK. They're developing a concept called Cassiopeia, which is a modular satellite designed for geostationary orbit to do microwave power beaming, and they've got backing from the UK government.
Okay, so targeting specific markets. What about in the US? Are we seeing similar approaches?
Absolutely. There's a company called Aetherflux. They're planning a constellation of satellites in low Earth orbit, LEO, designed for laser-based power delivery. But their target market is specifically remote terrestrial locations, think forward deployed military units, or maybe remote mining operations, places where getting power via traditional grid or fuel convoys is really difficult or dangerous.
That's neat.
And then you have companies like Reflect Orbital, which is pursuing a slightly different angle, putting giant mirrors in orbit to reflect sunlight down onto existing terrestrial solar farms, specifically after sunset, to effectively extend their operational hours into the evening.
Oh, reflecting sunlight. Clever. And the space-to-space power market is also starting to take shape, right? Powering things already in space.
Yes, that's another emerging area. For instance, a startup called Starcatcher aims to basically become an energy utility in space, selling power directly to other satellites operating in low Earth orbit.
Wow, an orbital power company.
Yeah. And another one, Voltaspace, is developing a lunar satellite network concept specifically designed to beam power down to assets operating on the moon's surface. This is aimed squarely at solving that critical challenge of surviving the 14-day lunar night, which is a major, major hurdle for any kind of sustained human or robotic presence on the moon.
That lunar night problem is huge. Okay, and of course, alongside these startups, government programs are still the primary drivers of the really fundamental SBSP research and the long-term, large-scale vision.
Definitely. In the United States, you've got NASA conducting comprehensive feasibility studies, like their recent OTPS report, and developing foundational technologies like advanced solar electric propulsion and, critically, in-space assembly and manufacturing techniques. Then you have the Air Force Research Laboratory, AVFR, and DARPA exploring potential military applications. And you can't forget the privately funded Space Solar Power Project at Caltech, which achieved those crucial in-space WPT demonstrations we mentioned.
Right. What about other major global players? Who else is pushing hard on this?
Well, the European Space Agency, ESA, has its Solaris initiative. They're laying the groundwork right now for a major strategic decision expected in 2025 on whether to commit fully to developing an operational European SBSP capability. They're involving major industry partners like the energy giant Enel Group.
Okay, big decision coming up for Europe.
Then there's China. They have arguably the most ambitious and centrally coordinated national SBSP program. Their roadmap includes plans for a LEO test system launching around 2028, aiming for an operational multi-megawatt prototype in orbit by 2030. They seem very serious about it.
2030, that's not far off.
Not at all. And finally, Japan's space agency, JAXA, has a very long history of SBSP research, particularly making significant progress in ground-based WPT experiments over the years. They're also aiming for some kind of operational system, potentially in the 2030s.
So it really feels like there are kind of two parallel races happening here, doesn't it?
Yeah.
You've got the public sector, the big government agencies chasing the huge gigawatt-scale vision, and the private sector startups tackling these near-term niche markets.
It's a really fascinating dynamic. You have these massive state-funded programs aiming for the ultimate prize, gigawatt-scale power to impact global energy supply and climate change. And then alongside them, you have these nimble, often venture-backed startups targeting specific, high-value niche markets that might actually be commercially viable much sooner, maybe even today.
Right.
But what's critical to understand is how they connect. These startups are effectively de-risking core technologies, things like WPT efficiency, lightweight structures, autonomous operations, and they're building the initial business models. This inevitably feeds into and helps accelerate the larger, more monumental government-led efforts. It's a classic pattern of how disruptive technologies often mature and find adoption. The small players prove out pieces, and the big players eventually integrate them into the grander vision.
That makes sense. The vision is incredibly compelling, the technology is advancing rapidly, brilliant players are involved, both big and small. But let's be honest, getting space solar power to a truly global scale involves absolutely monumental hurdles. Let's talk about overcoming gravity, starting with the elephant in the room, the economics, the sheer cost.
Cost is, without a doubt, the single greatest barrier. We mentioned it earlier, but it bears repeating. A gigawatt-class SBSP system, the kind that could meaningfully contribute to the grid, is envisioned to have a mass of thousands, maybe even close to 10,000 metric tons.
10,000 tons.
Yeah. Transporting that colossal amount of material from Earth up to geostationary orbit, which is over 35,000 kilometers up, it would require a sustained campaign of heavy lift rocket launches at a rate far, far exceeding anything the world has ever achieved before.
I remember seeing a NASA analysis that actually pinned launch costs as accounting for something like 71 to 77% of the total life cycle cost of an SBSP system. It's just huge.
That report really highlighted the scale. It noted that building just one large SBSP satellite might require something like 2 dedicated heavy lift launches per week for several years. Just think about that cadence. It dwarfs the total number of global launches from all nations combined in recent years. We're talking about an absolutely unprecedented scale of launch activity being necessary.
And this inevitably leads to a pretty contentious debate over the projected levelized cost of energy, or LCOE, basically, the cost per kilowatt hour generated over the system's lifetime. What are the current outlooks? I hear they vary wildly.
They really do. NASA's 2024 OTPS report, which took a hard look at this, presented a rather pessimistic outlook for near-term SBSP LCOE, estimating it somewhere between 61 cents and $1.59 per kilowatt hour.
Wow, compared to maybe 5 cents for terrestrial solar.
Exactly. That NASA estimate is anywhere from 12 to maybe 80 times higher than the projected 2050 costs for terrestrial renewables, which are expected to be down in the 0.02 cent to 0.05 per kilowatt hour range. So on paper, that comparison looks pretty stark, pretty unfavorable for SBSP.
Okay, that's the pessimistic view. But surely there were more optimistic takes out there too, right? Ones that paint a different picture.
Oh, absolutely. Studies from, for example, the European Space Agency and consulting firms like Oliver Wyman argued that the comparison isn't quite fair. They say SBSP becomes much more competitive when you compare it not just to raw terrestrial solar, but to terrestrial solar plus the massive amount of battery storage you'd need to make it a reliable 247 baseload power source.
Comparing apples to apples included the storage cost.
Right. That grid-scale battery storage can push the effective cost of reliable ground-based solar over $120 per megawatt hour, or 12 cents per kilowatt in some scenarios. So Oliver Wyman even suggested SBSP could potentially become more cost competitive than nuclear power or hydrogen turbines by the 2040s, if, and it's a big if, certain key technological and cost breakthroughs happen.
So there's a theoretical path to cost competitiveness, but it sounds like it requires a whole lot of things to go exactly right.
That's the crux of it. NASA's own report acknowledged an optimistic pathway where SBSP LCOE could potentially fall into the $0.03 to $0.08 per kilowatt range, which would be competitive. But getting there requires these unprecedented breakthroughs happening almost simultaneously across the board. Launch costs absolutely plummeting down to maybe $500 per kilogram, highly efficient electric propulsion for moving things around in orbit, hardware lifetimes reliably extending to 15 years or more in the harsh space environment, and achieving massive economies of scale in manufacturing components. It's like needing a perfect storm of technological and economic advancements all hitting at once.
A very, very tall order. And that's all just for the hardware in orbit. Don't we also need to factor in the ground infrastructure, the giant rectenna?
Absolutely. You can't forget the ground segment. That rectenna for a microwave-based system, as we mentioned, would need to be several kilometers in diameter. That requires a huge footprint of land, likely in a relatively remote area, and it adds hundreds of millions, maybe billions of dollars to the total system cost. It's a significant capital expense that often gets a bit overlooked in all the excitement about the space segment itself.
Okay, so the economics are daunting, to say the least. But even if somehow the money side works out, the engineering challenges are still just immense. What are the biggest technical hurdles we face in actually building these things?
Well, first off, just the sheer mass of materials challenge. We're talking about building structures weighing between 2,000 and 10,000 metric tons in orbit. This requires developing entirely new, ultra-lightweight, yet incredibly strong and durable materials that can survive decades in the harsh space environment. Every single kilogram you can save on the structure translates directly into millions of dollars saved on launch costs. Material science is key.
And the space environment itself is just incredibly hostile, isn't it? Beyond just needing strength.
Oh, it is. Radiation degradation is a constant battle. You have unfiltered solar radiation, high-energy cosmic rays coming from deep space, charged particles trapped in the Van Allen belts, all constantly bombarding the photovoltaic cells. This damages them over time, degrading their efficiency and ultimately reducing the operational lifetime of the whole system. While modern cells are radiation hardened to resist this, degradation still happens and significantly impacts the system's long-term economic life cycle. You have to build in that expected performance drop.
Okay. What's often cited as arguably the single greatest technical hurdle of all for large-scale SBSP?
That would almost certainly be in-space servicing, assembly, and manufacturing, or ISAM. Think about it. Assembling structures potentially kilometers across, made up of thousands of individual components, all in the vacuum and zero-gravity or microgravity environment of space. It's a capability that simply doesn't exist yet at anything remotely close to this scale.
We're talking autonomous robots building a power station the size of a city, basically.
Pretty much. It requires unprecedented advances in autonomous robotics, highly reliable remote operations, sophisticated artificial intelligence for coordinating the construction, and also for performing ongoing maintenance and repairs over the decades-long lifespan of the satellite. NASA is developing some foundational technologies like their print-assisted photovoltaic assembly process, but the leap required to go from lab demos to building an entire power station in orbit is truly immense. It might be the biggest single challenge.
And then there's the simple but complex problem of heat in space. Thermal management.
That's another really tricky one. A spacecraft in orbit experiences these extreme temperature fluctuations. It can swing hundreds of degrees Celsius from scorching hot on the side facing the sun to incredibly cold, deep sub-zero temperatures in shadow, all within a relatively short period.
Right, huge temperature swings.
These constant thermal cycles cause significant stress on materials and joints, effectively dissipating the waste heat generated by the power conversion process and just maintaining thermal stability across structures that might span kilometers. It's a huge engineering challenge that requires new approaches to material science, thermal coatings, radiator design, and overall structural engineering. Keeping the whole thing from warping or breaking due to temperature changes is critical.
Okay, massive technical hurdles. Finally, let's talk about navigating the geopolitical and regulatory cosmos surrounding SBSP. Because this isn't just about science and engineering, is it? It's deeply intertwined with international relations, law, and public trust.
Absolutely. You can't separate the technology from its context. A primary regulatory hurdle, especially for microwave SBSP, is spectrum allocation. These systems need a dedicated slice of the already crowded radio frequency spectrum to beam their power down without interfering with existing satellite communications, TV broadcasting, or other services. Securing international agreement on this through bodies like the International Telecommunication Union, the ITU, is a notoriously complex and often politically fraught process. Everyone wants spectrum.
Yeah, spectrum is valuable real estate, and adding these absolutely enormous structures to orbit will surely exacerbate the already growing problem of orbital debris, won't they?
They certainly would. Deploying constellations of massive SBSP satellites would significantly increase the overall collision risk in orbit. Just maneuvering these giants would be a challenge. And then, what do you do with them at the end of their lifespan, maybe 30 years down the line? Safely deorbiting structures that weigh thousands of tons, or moving them reliably to a designated graveyard orbit of this scale, and will require significant international cooperation and new technologies.
Right, end-of-life disposal is a huge issue. And then there are the undeniable national security implications, aren't there? Especially with the laser beaming idea.
Indeed. A nation successfully operating a gigawatt-scale power station in orbit would undeniably hold a powerful strategic asset. The technology itself, particularly the laser-based power beaming concept, has clear dual-use potential. It could, theoretically, be repurposed or perceived as a space-based weapon.
The space laser fear.
Exactly. This raises the very real specter of a potential arms race in space and highlights the urgent need for robust international treaties, transparency measures, and clear norms of behavior to govern the development and deployment of such powerful orbital systems.
Yeah.
How do we ensure it's used only for peaceful energy purposes? That's a big question.
A very big question. And finally, even if all the technical, economic, and geopolitical hurdles are cleared, there's still public perception. Regardless of the science, there will inevitably be concerns about safety down here on the ground.
You're absolutely right. Regardless of scientific assurances about the safety of the power beam's intensity, that it's no stronger than sunlight, for example, there will inevitably be public concern, maybe even fear, about the potential health and environmental effects of beaming high levels of energy down from space continuously. Building public trust and gaining regulatory approval for the large ground rectenosites will require a really proactive, transparent, and sustained campaign of public education and outreach. You have to bring the public along for this to succeed.
Absolutely critical. Okay, despite these truly monumental challenges, economic, technical, geopolitical, public perception, the potential impact of space solar power, if we can achieve it, is genuinely transformative. For our future, both in space and right here on Earth. Let's look ahead now at those future applications, starting close to home, relatively speaking, powering a cislunar economy.
Right. A self-sustaining cislunar economy that's basically the region of space between the Earth and the Moon, and especially any significant activity on the lunar surface itself, like habitats, mining resources locally, that's ISRU, in situ resource utilization, or doing in-space manufacturing. All of these things are incredibly energy intensive, and the big killer on the Moon is the 14-day lunar night. 14 days of deep cold and total darkness makes relying solely on surface solar panels with batteries profoundly difficult, maybe impossible, for continuous large-scale operations.
So space solar power, in some form, becomes the key enabler here.
It really is seen as the key. Various forms of space solar power, maybe satellites in lunar orbit beaming down power, or even Earth orbit satellites beaming to the moon, could provide that continuous, reliable electricity needed to power bases or factories through the long lunar night. This constancy, this reliable power, is what makes large-scale ISRU truly feasible processing lunar regolith to extract oxygen for breathing air, water ice for drinking, and rocket propellant, or metals for construction. Without consistent power, you just can't have consistent industrial operations on the moon.
And there's that powerful synergy we touched on earlier, the idea of actually manufacturing solar cells directly on the moon from local materials.
Exactly. Here's where it gets really innovative and potentially game-changing for lunar settlement. Researchers have shown that silicon, aluminum, iron, glass components, all needed for solar cells, are abundant in lunar regolith. If you can develop the technology to process this regolith and fabricate solar cells directly on the moon,
Using lunar power to make more lunar power.
precisely, it creates this incredible virtuous cycle. You use some initial power, maybe beamed from Earth or from orbit, to bootstrap the manufacturing capability. Then you use that capability to produce vast fields of lunar-made solar panels, which provide immense amounts of power for true self-sufficiency, dramatically reducing the crushing burden of having to launch almost everything from Earth. It could be the key to the sustainable lunar bases.
That's a powerful vision. And this concept of space solar enabling off-world operations could even extend to Mars exploration, couldn't it?
Absolutely. While Mars is further out and solar intensity is lower than at the moon, for settlements near the Martian equator, studies suggest that advanced lightweight solar arrays, perhaps combined with hydrogen-based energy storage systems, using electrolysis to produce hydrogen fuel during the sunny Martian day, and then fuel cells to generate power during the night, could actually be more mass efficient and lighter to transport all the way from Earth than comparable nuclear reactor systems needed for similar power levels. It all comes down to minimizing the mass you have to launch on that long journey to Mars.
Makes sense. Okay, so powering operations on the moon and Mars. Beyond planetary surfaces, space solar power is also set to revolutionize how we explore deep space itself, primarily through solar electric propulsion, or SEP.
Yeah, the maturation of SEP, which is directly enabled by having access to large, lightweight, highly efficient solar arrays, is going to truly revolutionize deep space exploration. SEP systems work by using electricity generated by the solar arrays to ionize a propellant, typically an inert gas like xenon, and then accelerating those ions out at very high speeds using electric fields.
So it's not a big chemical explosion, it's a gentle, continuous push.
Exactly. Think of it as extremely high fuel efficiency, like getting thousands of miles per gallon compared to a chemical rocket's maybe tens of miles per gallon, metaphorically speaking. It provides a very gentle but incredibly persistent thrust over long durations, months, or even years. NASA's SEP project is actively developing this technology as a cornerstone for its future deep space exploration architecture.
And the benefits of that high efficiency, that continuous thrust, are transformative for the kinds of missions we can do.
Absolutely transformative. SEP systems can be up to 10 times more fuel efficient than traditional chemical rockets. This has huge implications. It means missions can potentially launch on smaller, cheaper rockets because they don't need to carry as much bulky propellant. It frees up significant mass on the spacecraft for more capable scientific instruments or larger habitats. And crucially, it enables complex, long-duration missions with multiple flybys of different targets, or achieving orbits that would simply be impossible using only chemical propulsion due to fuel limitations. SEP is seen as key to making crewed Mars missions more affordable and making robotic exploration of the outer solar system far more flexible and scientifically ambitious.
Okay, so transforming exploration. And then finally, there's the ultimate prize, the original grand vision, transforming the global energy grid right here on Earth.
Right. If, and again, it's still a big if, but if SBSP can overcome those cost and technical hurdles, projections suggest it could become a major contributor to the world's energy mix, perhaps by 2050 or beyond, fundamentally altering the clean energy landscape. Its most crucial potential contribution is providing clean, dispatchable baseload power.
Dispatchable meaning you can turn it up or down as needed.
Exactly, and steer the beam perhaps to different receiving stations. It essentially solves the intermittency problem of terrestrial renewables by offering a constant, predictable 247 carbon-free power source. It could form that reliable foundation needed to support a grid running entirely on renewables.
And that level of predictable, clean power would lead to significant knock-on benefits for grid stability and maybe even national energy security, right?
Indeed. Having a predictable, steerable power source like SBSP could significantly enhance grid stability, making it easier to manage fluctuations from ground-based solar and wind. It could offer true energy independence for nations that deploy it, reducing reliance on volatile global fossil fuel markets. And it also opens up unique applications, like rapidly deploying power to disaster-stricken areas. Imagine beaming power into a region hit by a hurricane where the ground infrastructure is completely destroyed, or providing power to remote military bases, eliminating the need for vulnerable and costly fuel convoys.
Those are compelling niche applications too, and the sheer economic impact of actually building and operating a global SBSP industry would be staggering, presumably.
Oh, unquestionably. The development, construction, launch, and operation of a global SBSP infrastructure would be a tremendous economic and industrial catalyst. We're talking about creating potentially hundreds of billions, maybe trillions of dollars annually in new markets, driving innovation and high-tech employment across aerospace, robotics, energy material science, and many other sectors. It would be, in effect, probably the largest infrastructure project in human history.
Wow. Largest infrastructure project in human history. Okay, as we wrap up this deep dive then, it's really clear we're looking at two very different, yet, as you've shown, deeply intertwined frontiers for space solar technology. On one hand, we have the immediate practical application of solar power for spacecraft. That's a mature, rapidly innovating industry right now, with companies like Rocket Lab showcasing success by integrating capabilities and powering, over 1,700 satellites already in orbit.
Yeah, that's the established reality, constantly improving. And then on the other hand, there's that grand, almost mythical, distant vision of space-based solar power for Earth. And that path is still fraught with these immense economic, technical, and geopolitical hurdles we've discussed. The sheer scale required for gigawatt-class power delivery from orbit is truly beyond anything humanity has ever attempted to build before, anywhere.
Yet, despite those daunting challenges, the fact that governments, major corporations, and venture-backed startups are now seriously pursuing SBSP, that signals a profound shift has occurred, doesn't it? Something fundamental has changed.
It absolutely does. It signals that the convergence we talked about, dramatically lower launch costs, rapid advancements in high-efficiency photovoltaics like those exciting perovskites, the dawn of autonomous robotics and AI for in-space assembly has fundamentally altered the equation. What was considered almost science fiction or at best economically impossible just a couple of decades ago is now perhaps being viewed as merely incredibly difficult, which in the space business is progress.
Yeah, right. Merely incredibly difficult is achievable eventually. And crucially, these two frontiers, powering space missions and powering Earth from space, they aren't independent tracks. They really feed into each other, don't they?
Not at all. They're deeply intertwined. The burgeoning commercial market for powering assets in space satellites, stations, maybe lunar landers, soon serves as the absolutely crucial proving ground. It's where the enabling technologies, the lightweight arrays, the efficient power management, the robotics, the long-life components are developed, tested, and matured. Startups in this area de-risk the core technologies and build the initial business models and supply chains. And this inevitably informs, accelerates, and makes feasible the larger, more monumental government-led efforts towards utility-scale SBSP. It's a dynamic interplay, a necessary stepping stone.
So space solar isn't really a single monolithic goal then. It's more like a foundational capability that's evolving on parallel tracks, almost an inevitable consequence of our species pushing further out into the solar system.
That's a great way to think about it, indeed. Regardless of whether it's ultimately powering a small lunar rover digging for ice, or propelling a sophisticated probe to the outer planets, or maybe, just maybe, one day lighting up our cities from orbit. Harnessing the unfiltered, unending power of the sun and space isn't just an option for our future beyond Earth, it is rapidly becoming the essential prerequisite for it.
So maybe the final thought to leave you, our listener, with is this. As you think about humanity's future, both on Earth and off, what would it truly mean for us to fundamentally redefine our relationship with our star, the sun? To literally reach out, capture its energy where it shines brightest, and bring it down to power our world? It's a huge question, but one worth pondering as we look towards what might be a truly solar-powered future.